Yeah, it looks good. Okay, so first off, when I heard about this conference, I was like, oh wow, that's a great idea. We should definitely do something here in New York City. And then they told me when they were planning on having it. I'm like, well, that's really soon. How is this actually gonna happen so quickly? And I have to hand it to the staff. They've done a wonderful job. We should give them a round of applause. So yeah, there are a lot of great conversations I've already had with people here. If you want to continue or ask me anything about this talk, I'm open to emails, tweets, whatever. So let me know. If you can't count the D's, it's 4. So a little bit of a Lisp joke there. So I work at Jet. This is my favorite slide because I had that cool animation. I'll refresh it. It's kind of neat. That's actually done with CSS and SVG. Pretty cool trick I learned, so pretty neat. So Jet's kind of an interesting company. It's one of the few companies that actually uses F# entirely for everything. But this is an interesting language for the Elixir community because a lot of ideas actually come from F#. The pipe operator being one of them. So if you are curious about this, we should talk. Jet's also very, very much hiring. We help relocate people, and we pay very well. So let me know. So this talk really came from sort of my journey learning a lot of these things myself. I started in the Erlang community, and this was something where a lot of these things just had to be explored as I was dealing with problems or performance issues or trying to figure out why things worked the way they were, why the design was done this way or that way. And there's very little you can do when you really want to dig a little deeper than just the surface language. And so a lot of these things I'm trying to put together to help others. One thing I realized through this process, though, is that a lot of the source code it's actually worth digging into. And this isn't one of those things where I'm like, okay, let's go off, read the source code before you bother asking a question. No, this is very much a sort of habit. I've learned to actually start exploring the implementation of the tools I use on a regular basis. So with Elixir and Erlang, it's very much a very accessible code base. They're well organized. I'll just show you a couple of them really quick, just so you kind of see a lay of the land. We're not going to dwell on this, but it's worth seeing this, and it's worth taking in how easy it is to navigate. So I've got the Elixir repo right here. So it's pretty simple. At the top level, you can see in the sidebar, I hope, the lib directory is basically where most of the code is. So if we go in here, you'll see a number of subdirectories. These are major units. The main one I've explored is Elixir itself, but if you're interested in the interactive shell or all of those things, these are actually really easy to get into, very well documented. Now, you'll occasionally see source directories, and I'm sure a lot of you are familiar. That's generally the pattern for Erlang projects. You put your Erlang code into source, and you put your Elixir code into lib, and there's sort of a convention. But here you can basically see a bunch of the initial Erlang modules that implement a lot of these things. So I have right now pulled up a file. We'll get into this extension a little more, but elixirparser.yrl. So this is one of the files in here, and it describes a good chunk of the language you see every day. So a lot of these are pretty self-explanatory, so I'm not going to go too much farther. Let's take a quick sidestep over into Erlang. Erlang OTP on GitHub has this layout, and it's not too different. Lib here isn't for Elixir code, though. It's for just the standard bundled applications or libraries or whatever you want to call these containers. This is pretty well organized. So if you want to see stuff related to compilation, you can go to compiler. If you're interested in eUnit. You can jump into that, or even if you really want to, you can look at hype, maybe not. So yeah, compiler here is a very useful one to get into because a lot of the code is actually very well documented. It's just not exposed. You can open up the Erlang documentation and not see a lot of this stuff. So under here, you'll see all sorts of stuff. Beam assembly, you'll see stuff related to C-Erl, which is all about the Erlang AST. You'll see stuff around core. This is Erlang core. There's something called kernel. We'll get into that and explore that a little bit. These are all very useful things, and you can use them as a library. Some of them have more friendly APIs than others, but a lot of them are very well documented. Some of them less so. This one is a bit hit or miss, so you'll have your own mileage there. One thing I'd quickly, before I jump into the rest of the talk, just to show you sort of the simplicity of a lot of this code, one file I like to point out to beginners is gen.erl. A lot of people know about gen servers and gen whatevers. How do they actually work? When I do a call or something or a cast, what actually runs? Well, you can open this file. You can open the others too and explore, but what ends up getting called is this. So if you do a call, it does this try monitor thing, and then it explains all of the cases of what happens when the process isn't there and we fail to monitor. What do you do? And you can quickly see all of the edge cases and why it works the way it does. It's really educational. It's very much worth diving into this. Okay, so let's go back. Sorry, let's go back here. So why this talk? I've sort of described my own experience getting into this, but why did I even need to know some of this stuff? Sometimes some of these details really do matter, whether it's performance or you're getting some weird error, or maybe you even want to know why something's seg faulting. The other reason is more and more, all of these other languages are starting to be targeting the beam. For a while it was just Elixir, it was alone, and now we have all sorts of languages, LFE, a bunch of other experimental ones I'm starting to see pop up. It's really great to see these, and understanding how you can use them or how you can contribute is a really worthwhile thing to jump into. And honestly, coming from the Erlang side, it almost seemed like, oh, we've been fine. We don't need Elixir. But really, these languages need each other. Erlang's very important for Elixir, and everything eventually goes through all of the same pipeline and tools. But likewise, the other way around. There's so much benefit the Erlang community gets from Elixir. So I highly recommend treating it as a two-way conversation and not thinking of your languages as isolated. You'll be a much better Elixir developer, I promise, if you learn Erlang. So I highly recommend this. So let's look at the roadmap we've got. So parsing, ASTs, macros, protocols, these are probably things you've heard of or see in the docs. These are pretty well covered. I'm going to go through them so you can kind of see the entire pathway. But these should be relatively familiar. For beginners, maybe you'll learn a little bit, but I don't plan on diving extremely deep into these topics. What I really want to go through are the next three. All of these intermediate representations, transformations, what's optimized, where does optimization happen in Erlang? Beam assembly, you see these beam files, what are they? What do we know about them? Are they useful to manipulate or look into? And then what happens at runtime? There are some nice little things to know about there as well. So we're going to use this little vehicle, a really useful piece of code. Yeah, maybe. So the FizzBuzz example is actually purposefully really trivial. I want to show this because there are so many things in a piece of code that you think would not really matter or not really relate to compilation. We'll start seeing a lot of these things come out as we see all of the conversions and intermediate forms come out of this. So this may look trivial, but we'll learn quite a bit just from this simple code. So we'll start with parsing. I've already shown you a little bit of that grammar from the language. So this is called a YEK file. And that comes from YAK, which is yet another compiler, which is a C tool. When you want to build a parser in C, you might use this if you need a LALR style grammar. I'm not going to get into what that is. You can Google it. But these tools allow you to easily build languages, and both Elixir and Erlang both use these tools to parse their code. Here you can see a very simple example. You have a term name, map operation, and the literal. These are just empty maps, two different forms. Believe it or not, the end of line needs to be there to disambiguate. So the grammar definition is under 1,000 lines, but there's a lot of stuff. I'm not going to go through every line. There's a lot of stuff that seems to be missing. And so where does the rest of the language come from? You might feel a little shortchanged if you sit there and really try and understand all of that grammar. You know, maybe the part of the language you were curious about isn't showing up there. And that's because of macros. A lot of what you see, you know, def module, all of those sorts of things are actually just macro invocations. They follow that same syntactic form, you know, the do-end sort of structure. This is key to making Elixir very easy to build in Elixir, because most of these things can actually just be written as macros. It makes it very, very easy to explore the language as well. One thing we can do when we're exploring is quoting. We can quote anything in Elixir. We could quote an entire module definition if we want, but it doesn't quite fit on a slide. So here, I just quote one part of our code here, and we see that we've got a bunch of terms. They're not very easy to read, actually. It's a lot of metadata in between, but basically, if I just single out one part and remove some of the noise, this is no longer exact, but it's for illustration. This range that I build, 1 to n, becomes this highlighted portion down here. So this part is very, very quirky looking, but it's easy to understand once you realize that these tuples have a few parts. Here we have the symbol ... which is the operation we're doing, and then we have the parameters to that. And there are two parameters. There's the one that comes on one side of it and one that comes on the other. Not all of these things that we're calling are, you know, these sort of infix operators, but in this case, it is. But in the AST, it doesn't matter. We put everything this way. Any sort of function call, any sort of application happens in this order. And so we can see that we simply pull out our one and then our variable n, and that's it. It's very, very simple. This Elixir here is sort of a context that we're dealing with. There are some name lookup rules. I'll get into that in a second. Something to know about these macros, very useful thing, is the hygiene. Macro hygiene sounds kind of like a inconsequential feature, but it actually makes it a lot easier to ensure that you do things correctly. Variable names might be quoted as one name, but when you unquote it, it will ensure that you don't clobber any variables that are coming from a different lexical scope. So it will rename things slightly. And we'll see this all over the place. We have other sorts of renaming in Elixir as well. For example, when you reassign a variable, you're not really reassigning the variable. Under the covers, what it's doing is it's creating a new variable with a new name that just looks like the old variable, but it's actually an entirely new name. And underneath, the AST will start treating all of these new instances as new names. Macros work a very, very similar way. There are ways to escape this from macros. You can't do this for a lot of other things. Variables are always single assignment underneath. We'll see why. One useful thing to mention is env and collar. You may have seen these if you get into metaprogramming. I'm just going to run this really quick. Spits this out. It's a structure that has a lot of interesting fields, but it basically explains why code behaves the way it does in that context. Here we can see we have a lot of the interactive shell helpers. C and clear and flush, ls. We can also see that we have a few macros. H is a macro, for example. So useful to explore. I'm not going to spend a huge amount of time interacting with that, but definitely try it in the shell. There's a lot of stuff you can also do with the code module. I'm going to skip past that. So one more thing we have, protocols. Struct is an interesting hidden field when you have these custom values, which allow us to effectively build new types. So if I take this env and just say struct, just to show something we already had, the type here is macro env. So now we know what kind of thing Elixir is going to treat this as. And what this is useful for is protocol dispatch. What we want is a way to say, I've got something that can take multiple types, but I want to define one operation for a specific type at a time, rather than having to handle all cases at once and do some giant pattern match for every single case. This allows extensibility. It allows a lot of horizontal scaling of code. And so you'll see a lot of people complain about, oh, I've got this performance problem. This is another thing to look into. You need to remember when you deploy production code that you want to optimize this mismatch on the protocols by compiling these back into one module, so it doesn't have to go in directly to the module and look up the operations and see if they're defined or fall back to the default. A lot of this gets a lot faster if you do that right. Okay, so it's time to switch gears. There's a lot past this step, and so we're going to sort of think a little more in terms of Erlang. You'll see some Erlang code. Occasionally, I'll use Erlang term syntax, which is almost exactly the same, so it should look familiar, and explain a few things. So one thing we can do, we can compile this code that we've already got. So let's say I ran elixir c on my fizzbuzz.x file. It will generate this beam file. And I can use this code right here to extract an AST. And this looks something like this. It's pretty big. It's going way off the screen. I'm not going to go through it. So maybe we'll just focus on one part of it. I've got that count function, except the count function actually had an optional argument. So I've got two function clauses here. So what's happening here is it's actually synthesizing two different functions. Count does not take variable numbers of arguments. It takes one set, and it will distinctly generate one that expects a certain number of arguments and then knows the special cases for defaulting the ones that were left off. And so this is how those default arguments work. We can see here at the top that we have our default 100 passed in here, and all we're doing is this call. These numbers right here are line numbers. It's almost random that they just wanted to put a second, but yeah, they just go there. And then we see that we have an atom count, and we're just calling that atom. It's a local call just inside of the module with the integer 100. We jump down here, and we now see that we've got much more sophisticated code. We see a variable, the variable n at 1. Here's the first example that we'll see with variable renaming. This is not the variable we put in our code. It's now something different. If I reassign this somewhere in that function body, you'll see that at 1 change, usually at 2, at 3, and so forth, but sometimes it's a little more complicated than meets the eye. So there's a lot of stuff we can do with this AST, and I don't have near enough time to go through it, so I'm just going to sort of speed past a little bit of this. But I do want to give you a flavor that there are some interesting things. Sorry, a little too fast there. Some interesting things. Specifically, there are parse transforms, which you may not see ever, but if you hear about it in an Erlang library, this is basically the idea of taking a module's full AST and returning a new full module AST. So instead of quoting a form, like Elixir macros do, this just recompiles a whole entire module. It's kind of brute force. It's very powerful, but it's overkill for most small expressions. So this is why you see in the Erlang community a little bit of a do not use parse transforms. Even if you need to, just don't. Just don't. You know, and you still have a few cases. There's some good ones like Logger, a really great logging library, but these days, even now, you don't need it anymore. There are even better ways to implement the same features. So more and more, I think this will go away. So we have this AST. Let's do a little experiment. We can take this AST and turn it back into Erlang code. So I had to truncate a bit of the file because it generates, you know, the under info stuff for documentation, lookup, and all of that. So there's some of that. There's other spec data. But here's what this Erlang looks like after running this little thing. And yeah, sorry for this function. It's sort of cut off by my slides. So you can see the whole thing there. It's a little bit of a line. I will definitely share these slides so people can look at this and they don't have to memorize or write down this code. The thing here is this isn't valid Erlang code. This is invalid. We have n at 1 down here, and I'll tell you that does not compile in Erlang. It should at least be capitalized, and the ats are definitely also a problem in most cases. So we need to fix this. I can take all of these, and I can replace them, and maybe reformat the code a little bit to look something like this. A little more familiar, but you notice there's something odd here. We have this elixir enum each map range new. It's everything we know, but the syntax is different. Pipelines are missing. Erlang doesn't have some of these nice features. This is definitely something you start missing when you're in the Erlang world after having used stuff like the pipeline operator. So we see that we have this recursive nesting call of all of these constructors, and it still doesn't feel like how I would write it in Erlang. So just for kicks, just show something slightly more idiomatic, doing mostly the same thing. List comprehension. Right here, we're taking a sequence 1 to n. This says, OK, and now on the other side, I want to do something for it. And so it prints out the converted representation of all of those. So effectively, this is what it's going to look like in Erlang code. Now, why did I go through the trouble of doing all of these little adjustments and steps? Well, we're about to jump into yet another layer of this, and unfortunately, right now, it's very hard to force the Elixir compiler to emit some of these intermediate formats directly, whereas the Erlang compiler makes it a lot easier. There may be some room for some tools, and possibly we can just make this a library, but it makes a lot of sense to add this to the Elixir compiler, and I think with the right contributions, I'm sure we could get that in. Oh yeah, sorry. Oh yeah, one other thing I wanted to mention really quick. This is sort of interesting. The modules have a lot of interesting properties. You can actually share code and constants across processes. People don't tell you this. But you use it as code. Code is basically the only thing you share across processes. And there's a library called Merle, and you can use this just as easily via Elixir, so I highly recommend checking this out. So now we can just turn this into bytecode and run it, right? I mean, it's basically what most other languages do, or something like that, right? Not quite. So we have core Erlang. This is our first stop after the AST. This is yet another language. It's designed to remove features and simplify things. A lot of features of a language can be rewritten as a set of simpler features. And so we're trying to reduce the language to the minimal things we need. And so this language is much, much simpler than even Erlang. So let's look at how we get this code. So there are two main ways, two easy ways at least, to get this. It's with compiler flags. You can either do it with +2 core while you're compiling, or you can, in your shell, use the C command, pass your module name, and call 2 core here. This does not load or generate a beam file. In fact, you may even get a little warning in your shell when you do this that it's not actually generating something. It's generating a core file. So this core file has a syntax. Now, I called it simple. This language is simpler, but it's not really designed for humans to be reading or writing, at least in this format. Usually you keep it in the abstract AST that represents this language. But here we have a nice visual representation. It's better than using tuples and trying to explain that format. But you can see that a lot of things just become very explicit. We don't have sugar for anything. A lot of things become very, very simple. We have a lot of these fun calls. We have a limitation to the number of statements we can have after each thing. So you see these do calls, so we can actually chain things together and run lots of things one after the other. If you have a lot of steps, you'll see a lot of these do calls in your code. But this is effectively what the code looks like. I'm also skipping some of it. I've removed a few bits that are noisy, but I've left one interesting thing, and you'll see this like turnstile or tack operator here. This thing is interesting. It's useful because it allows metadata to be added by the compiler. This metadata is used by all sorts of things. In this case, it's just saying that this code was generated from a list comprehension. It's quite a bit uglier, but yeah, we'll get into some of the interesting factors of that. So as I mentioned, you don't want to type this in. You definitely want to just generate it and read it. Sometimes you may want to go through an editor and try and clean it up. Most of all, you want to have a specific thing you're looking for, like a function or two. If you try and take your whole project, turn it all into core, and then just read it that way, you're going to be very disappointed. It's not fun. Okay, so optimizations. This is an interesting part of core. This is basically the primary place where most of your code optimizations happen. The main one people know about is inlining. Function inlining is a common way to optimize virtual machines. Just-in-time compilers do it all the time. Ahead-of-time compilers do it. It's really, really, it's the bread and butter of optimization. So this is where it happens. This will take small functions that it feels like won't add too much bloat to the code, so you're not expanding the amount of code you have in memory, and tries to just put them straight into the call site. Now, in order to do this, it needs to be a local call. You cannot do the remote explicit call with the module, which works with reloading, so you need to be careful about this. If you want inlining, you need to make sure you're using the right call forms. So consider hot loops versus non-critical code paths. You can treat it differently. This goes hand in hand with constant folding. Constant folding is very important. It basically eliminates a lot of the obvious overhead that you have once you inline that code. A lot of code seems like it can't be removed until you have some constant that you're passing into something, and then suddenly half the code just melts away. Like a conditional branch somewhere might just disappear because it knows that it's always going to go through a certain path. Tuple operations, some of these things are newer optimizations. This one specifically has some improvements coming in version 19 that's in release candidate status. It's really exciting to see these start to expand. This is going to be a great release. Another interesting one is list module calls are optimized. Unlike most modules, lists in Erlang are treated specially, not just the type, but the actual lists module. These calls will be inlined. These calls will be treated very differently because no one ever reloads the list module. It's pretty much static. So we'll go past that. So we still can't jump right into that. So I have two more steps. We'll be very, very close to running it. Kernel Erlang is one more intermediate format. This one is even simpler, you could say. Maybe it also looks a little simpler, so let's generate it here. Same sort of convention here. We have two kernel. Two kernel effectively is just like two core, but yet another language. And it generates something like this. Maybe it looks a little nicer, actually. I've reformatted it a little bit here, but this is mostly what you get. Part of the reason it's nicer, though, is because it doesn't, this format, when you generate the language, not look at the AST, does not include all of the metadata. So you're missing some information here that the compiler actually has. So you shouldn't take this as fact sometimes. There's more data around it, but this is still useful to understand the steps that are going through to change your code. Here we have our counts again. You can see the the calls in the body here. One is remote, and the other one's local. Now we have this interesting thing here. It's got this dash in front of it. Sometimes, if you've seen a stack trace, for the cases where Erlang doesn't always work, you may notice these weird names. These pop up occasionally. They used to pop up a lot more, but they improved that with line numbering information. But this is a very useful feature to know about. So yeah, let me actually, sorry, I think I may have gotten that slide. Okay, shoot, I think I may have screwed up my slide deck. But anyway, this is called lambda lifting. This is actually an anonymous function, effectively. Our list comprehension generated some sort of closure, that body that we were executing as we looped through. This anonymous function needs a name because the compiler needs to say, I need to jump to that code. And so effectively, what we're doing is something called lambda lifting, which allows us to address things that were otherwise anonymous and pull them out of the code body that they were defined in. This is very, very important for code generation. Makes it much more efficient. It also does an application optimization. You'll commonly see something in Erlang. This is not available in Elixir, but it's an interesting contrast where you can actually use variables for your module and function targets. These will be atoms, and then you'll have your regular argument list. And these basically turn into an Erlang apply call. MFA, if you see these in documentation, are a common triplet. Module, function, arguments. So we're about ready to jump into the Beam assembly, but before I do, I want to describe a little bit of history. The Beam is inspired by a family of virtual machines of Prolog lineage. WAM, or Warren's abstract machine, is the specific one. There are a couple Warrens in Prolog history, but this specific guy has contributed quite a few interesting things. And a lot of this was so popular that during the era of development that Erlang came around, and it just basically picked this up as this is the best way to build a VM. And today it still stands up. The X and Y registers are things you'll see. The X stands for ordered parameters. These are things you're actually passing between functions. The Y registers are just indexing into your stack space for that call frame. So we'll see how this plays into. So when we access a function by calling it, we basically need to make sure we set up these X and Y registers. So if I have a value in X0 and a value in X1, and then I do a call to another function, I need to make sure that the registers are set up in the right order for that function to then receive those arguments. If they're in the same order, they're going to basically be called right away. You don't have to do any operations to move things around. Otherwise, you have to shuffle, and this is just going to slow down the virtual machine. So you'll notice if you really want high-performance Erlang, you should also be very careful to make sure your argument order lines up so your registers don't have to do any shuffling. So we can now I think we're ready to generate our assembly file. So to ASM is what we want in this case. And it will give us something like this. This looks like a sequence of Erlang terms, basically. Each thing is delimited by a period. The reason for this is that it is actually a binary format. It's never actually serializing these terms directly. And we can see that we have these registers and these operations. I'm not going to go over all of them. I don't have enough time, but oh yeah, here, I forgot I moved lambda lifting to this section. Here you can see the example of the function being lambda lifted into this separate thing. If you go to this file, you'll notice that this is now at the top level. It is not nested inside of count. Beam files can be zipped, so I'm not going to go into a huge amount of detail here. It's a very useful feature. eScripts sometimes run as archives. So we're almost done. the loading of the Beam code is actually a surprisingly complicated process. Sometimes people complain that their programs don't load fast enough. It takes a second. If you run Erlang or Elixir programs on a Raspberry Pi, you may notice that it's just a little slower sometimes. This is not easy to notice, but once you realize what's happening is there's another transformation step happening every time you load your code. First thing that happens is something called instruction fusion. It sounds pretty cool. It actually is a pretty neat idea. It's the ability to take all of these Beam assembly instructions and rewrite them into others, and we'll see an example in a second. The other thing we do is direct threading, and I just need to show the example to explain it. So in order to get the code in the example, we have to use this ERTS, Erlang Runtime System, debug module. This is also mostly undocumented. This is really, really important. It's basically the best tool you can have that's undocumented when you really, really need to know why something is working the way it is or why something's taking more memory than you expected. It's got all sorts of great tricks. The specific thing we want is df. I believe dump forms or something like that. I'm not exactly sure what df stands for. But here we see the output, and this is in a file, fizzbuzz.dis. Finally, we're to real code here. This is actually what's run. These on the right are our functions, and then on the left, we have these addresses. These are actual pointer addresses in memory. This is where your code is living. And the reason for this is it will actually jump directly to that address in memory rather than looking it up in a table. This speeds up the virtual machine quite a bit, and this is one of the reasons why you see a huge amount of performance. The careful instruction design fuses together operations that are really common, that come together, and this is the other half. This is really why you get a lot of efficiency. There are these patterns that happen over and over and over again, creating a tuple that has 3 things. You don't want to create it and add the one item and then set another element and then set another element, and now you have 3 tuples you've created just to create that initial data. That's a lot of allocation and overkill. So this is where we really get that efficiency back, and it knows to find those common patterns. Yeah, there's a lot I could talk about here. There's a lot of miscellaneous areas that relate to this. Hype, ahead of time compilations, some of the ongoing work on JITs, stack frame efficiencies. There's a great efficiency guide in the Erlang documentation that I highly recommend you read. It debunks a lot of ideas that people think need to be done by hand that are just no longer really true. And with that, I'll open it up to questions.
Questions for Brian? Our journey to the center of it in the back?
Yeah.
Hi. So in the slide you just showed with the action memory location information there, has anyone adapted the compiler for address-based layout randomization?
Yeah, I'm not sure
Could you
about
repeat
that.
the question?
Oh, yeah. So what he was asking about is if anyone has worked with address-based randomization. So the idea would be that you can load your code anywhere. And since you're creating this map as you load the code, it just depends where the code segment for the Erlang virtual machine, the C code that's been compiled to your native architecture, lives. And I think this would effectively work if your C code is randomized. It shouldn't break because you can effectively at runtime take the address of whatever function or label in the GCC sense of direct threading. That address that you're jumping to, you can just get it at runtime and it will know where it's been moved to. So that should work just fine. Yes?
Earlier on, you talked about function inlining, inline optimization only working with local calls. I'm wondering if that's local module or just importing a module out of the pipeline.
So it is local to a module outside of specific cases with lists. That's one thing where sometimes I do wish I could tell it, yeah, really, if I upgrade this code, don't worry, I don't mind having a stale copy. It'd be nice to have an option to increase that list and include more kinds of modules. But at that point, you're really getting to a really low level of performance tuning, and it's usually not a bad idea to copy things locally when you really need that extra performance. And honestly, you should not go out of your way to use some of these techniques. They're something you want to measure as usual. The usual, please benchmark it first. Don't just go trying to inline and avoid remote calls. Remote calls are useful because that's how code upgrade works. So, you need to balance things, but it's good to know how it works.
We'll do one more.
So you mentioned like the argument ordering. Have there been any other things from like diving into like the VM that changed like the code didn't write?
Yeah, so outside of argument ordering, are there any other things I've changed in the code I write? I guess the basic idea that I've realized, and this is an interesting point, because the Erlang virtual machine is not designed to be a general purpose virtual machine. It was designed next to Erlang. They grew together. They're almost one and the same. And so a lot of the good idioms in Erlang are well supported by the VM, and you start noticing that when you write idiomatic Erlang code, it works better, it's more efficient. Elixir does a very good job embracing this, and allows you to write what would be idiomatic code in a new and more advanced way, and I think that's a really great part of how Elixir's emerged, and it's very, very important. All right.
Thanks, Brian, for that journey to the center of the beam.
Thank you.
Yeah, I'm never going to get tired of saying that.